Hi everyone. So in this video, we're going to begin with chapter 4, exponential and logarithmic functions. First of all, let's talk about the learning objectives. By the end of this chapter, you should be familiar with exponential functions and their graphs, concepts of exponential growth and decay, and applications, the nature and significance of the number e, or Euler's number, logarithmic functions and their graphs, properties of logarithms, solving equations involving exponential expressions, and solving equations involving logarithmic expressions. So let's start with section 4.1, exponential functions. And we're going to talk about the characteristics of exponential functions. So here, they are comparing two equations, y equals x squared and y equals 2 to the power of x, which are both similar in the sense that they both have a base and an exponent or power. So in y equals x squared, the base is a variable x, and the exponent is constant, it's 2. Whereas in y equals 2 to the x, the base is a constant 2, and the variable is x. So x squared, y equals x squared, is a parabola, right? It's not an exponential function. So y equals 2 to the power of x would be an exponential function. The main thing here, the fundamental difference between exponential functions and power functions is the fact that if you consider values for x for both of these equations, as you can see here in table 4.1, you can see that the exponential function grows at a much faster rate. For instance, if you take 10 to the power of 2, that's going to be 100, whereas 2 to the power of 10 is 1024. So now let's talk about graphs of exponential functions. The graph of any exponential function, f of x equals b to the power of x, where b has to be a positive number and b cannot equal 1. Why? Because if b equals 1, it's just going to be a constant. So in example 4.1, they ask us to graph each exponential function by plotting several points and then drawing a smooth curve through the points. So I would invite you to stop the video here and do this on your own. Pick values that are a little bit lower than 0 and a little bit higher than 0, and graph both f of x equals 3 to the x, which is example A, and example B, which is 1/3 to the x. So if you did this correctly, this is the shape of those two graphs that you would get. And in this case, they took integral values of x from -3 to 3. So notice that x to the -3 for the case of 3 to the x is going to be 1/27, whereas for 1/3 to the x is going to be 27, and then so forth. So notice that really what you get is a reflection across the y-axis. Now, if you remember from a previous chapter, we get reflections across the y-axis when we have, in this case, let's say we have y equals 3 to the x. A reflection of this function across the y-axis would be y equals 3 to the minus x. But notice that this is the same as saying 3 to the minus 1 times x. And this is the same as saying 1/3 to the x. So therefore, 3 to the x and 1/3 to the x are the reflection of each other across the y-axis. So now let's take a look at the properties of exponential functions. If b is greater than 0 and b is not equal to 1, an exponential function with base b is a function defined by f of x equals b to the x. So the domain of f is the set of real numbers. X belongs to R. And the range of f is a set of positive real numbers, y greater than 0. The graph of f passes through 0, 1. That's because anything to the power of 0 equals 1, right? The x-axis is the horizontal asymptote, and depending on the value of the base of the exponential function b, it will either be continually increasing, which is called exponential growth curve, or continually decreasing, which is called exponential decay curve. So this would be exponential growth, and this would be exponential decay. So this is where b is greater than 1. That's the case of exponential growth. And notice that as x increases, the function f of x tends to go to infinity. And in the case of exponential decay, the main difference is that b is a value between 0 and 1. And as x increases towards infinity, f of x gets closer and closer to 0. So now let's talk a little bit about transformations of exponential functions. If you recall from section 1.5 how the graphs of functions are translated and reflected, we can efficiently sketch the graph of many exponential functions. So in example 4.2, they ask us to use the graph of f of x equals 2 to the x to sketch the graph of each function. State the domain and range for each function and the equation of its horizontal asymptote. So recall for letter A, this just means 3 units up for every y. For letter B, this is going to be a reflection across the y-axis. For letter C, we're going to have a reflection across the x-axis. For letter D, we're going to have a horizontal translation of 4 units to the right. And then for letter E, what we're going to have is that every y value is going to be multiplied by 3. So actually, let's take a look at the graphs themselves and explain what would be the domain and range, as well as the horizontal asymptote. So for letter A, the graph of 2 to the x plus 3 can be obtained by translating f of x equals 2 to the x vertically 3 units up. We can see that the x values are not affected, but the y values are increased by 3. Notice that here we have this point on the red line, which represents 2 to the x, with coordinate 0, 1, and then the blue line representing 2 to the x plus 3 now has coordinates 0, 4. And then what used to be 2, 4 is now 2, 7. Now we're going to have that the domain of G is all real numbers, and the range is now going to be y greater than 3, and obviously the horizontal asymptote is now going to be y equals 3. For B, like we said before, 2 to the minus x is simply going to be the reflection across the y-axis. We can see that here. The domain is going to be the same, x greater than, no, 1, 2, 3. The domain is going to be x belongs to the reals, and the range will be y greater than 0. The horizontal asymptote would be the same, y equals 0, which is the x-axis. For C, the graph of p of x equals minus 2 to the x can be obtained by reflecting the graph of f of x equals 2 to the x in the x-axis, as we can see here. So notice that now every y value is going to be the opposite of what it was before. The domain is going to be x belongs to the reals, but now the range is going to be backwards. Y is less than 0. The horizontal asymptote is the same, y equals 0 or the x-axis. For D, we said that the graph of 2 to the x minus 4 can be obtained by translating the graph of 2 to the x 4 units to the right. So we can see that here. What used to be 3, 8 is now 7, 8. What used to be 2, 4 would now be 6, 4 over here, right? This would be 6, 4. And then 0, 1 becomes 4, 1. Domain and range don't vary. And the asymptote, the horizontal asymptote, is again the x-axis. And then finally, Letter E, the graph of v of x equals 3 times 2 to the x can be obtained by a vertical stretch of the graph by a scale of factor 3. Now, that just means that we multiply all y's by 3. So what used to be 0, 1 is now 0, 3. 2, 4 is now 2, 12. The domain and range don't vary, and the horizontal asymptote is still the x-axis. So next, let's take a look at example 4.3. And it says, a sample count of bacteria in a culture indicates that the number of bacteria is doubling every hour. Given that the estimated count at 1500 was 12,000 bacteria, part A, find the estimated count 3 hours earlier at 12. Okay. Now, the thing about these exponential functions is that really they are the same as a geometric sequence. But since we're talking in terms of functions, we're going to have to use a function terminology. So let's say amount of bacteria in time t is equal to an initial amount times the ratio, which is 2, to the power of t, which is the time in hours. So since they want us to find the amount of bacteria that was there at noon, that means 3 hours went by, right? So let's look at it this way. Let's say that at t equals 0 occurs at noon. And 3 hours later, at t equals 3, we get that the amount after 3 hours is equal to 12,000. So that means that 12,000 is equal to a sub 0 times 2 to the 3. In other words, the initial amount is going to be 12,000 divided by 8, which equals 1,500. Therefore, that was the initial amount of bacteria, or that was the amount of bacteria that was present at noon. For B, they want us to write an exponential growth function for the number of bacteria at any hour t. So that's just going to be substituting here, right? In other words, it's going to be A at any hour t, amount of bacteria at any hour t is going to equal 1,500, which is the initial amount. We take that as the starting point, times 2 to the power of t. So next we have example 4.4. And it says an initial amount of 1,000 euros is deposited into an account earning 5.25% interest per year. Find the months in the account after 8 years if interest is compounded annually, semi-annually, quarterly, monthly, daily. So annually is compounded once a year, semi-annually is twice a year, quarterly is 4 times a year, monthly is 12 times a year, and daily is 365 times a year. Now this is very easy because we did this before. This is simply applying the formula for compound interest. So remember that it's going to be amount equals the principal times 1 plus the rate divided by the amount of times it's going to be compounded to the power of the amount of times it's compounded times the amount of years. So in this case, it's going to be 1,000 euros and then 1 plus the rate. Here's where you have to be careful. This is going to be 0.0525. That's 5.25% divided by n to the power of n times 8. And then all you have to do is substitute n for 1, 2, 4, 12, and 365, and you would get all the answers. So you might want to stop the video here and do it yourselves. So here are the solutions. Just compare to see if you got the same answers. Notice that when you talk about money, you have to round to 2 decimals. So now we're going to take a look at example 4.5, which is the last one on this video. And it says a new car is purchased for $22,000. If the value of the car decreases or depreciates at a rate of approximately 15% per year, what will be the approximate value to the nearest whole dollar in 4.5 years? So there's several ways to do this, but let's approach it from the point of view of a simple interest formula. So normally the simple interest formula is amount is equal to the principal times 1 plus the rate to the power of t. But this is when the value of money is appreciating, right, in banks. But in this case, it's depreciation. So instead of plus, we're going to have a minus. So let's write it as A is equal to P times 1 minus the rate to the power of t. So for this particular problem, the car starts with a value of 22,000. It's going to be 1 minus 15%, which is 85%. So 0.85 is going to be the rate of depreciation. And what's going to be that final value of the car in about 4.5 years? So if you plug this into the calculator, you're going to get that it's going to be approximately 10,588. So the solution is in dollars, right? So $10,588. We write it exact because they want the answer to the nearest whole dollar.